Thank you. Yeah, I'm looking forward here to give you a blitz update on the developments we have done with PETfilms for flexible electronic applications. And we are a company which is a global company, which has 6 manufacturing sites across the world, with an R&D center where I personally work in the UK, northeast of England. We've been a long time in developing films for application in flexible electronics, since the early 90s with test strips, batteries, membrane touch switches, flexible printed circuits, diffuser, reflector films. And you may wonder why, actually, apart from being a choice for sustainability point of view these days, why we actually use PET. Now, briefly, it's because of our process, really, or by actual orientation process with the crystallization at the end, that gives us superior properties for chemical, electrical, mechanical, and optical. And but not to go too much in that, what I want to show you though is the scale of the production here. We're making from 0.5 micron to 500 micron thick films with run rates from 20 to 300 meters a minute, and on a line of 9 meters wide, that'll give you 2,000 square meters a minute. That's a large scale, but allows us to offer it at low cost, but has repercussions for minimum order quantities, of course. Now, many applications in the flexible printed electronics rely on DTF's dimensionally stabilized grades, and they become more and more common with development of low temperature solders, and therefore we can move away from the more expensive high temperature resistant substrates, also polyamide. We have a more superior polyester film, which is PEN, which is mechanically stronger, higher processing temperature, and better weather resistance. Basically, this is really why we are in flexible electronics, but more so we are in it because we happen to be able to tailor our substrates to your specific needs by functionalizing it through modifying the properties of the bulk. We have multiple layers of different polymer grades, or we can add treatments for a functionalized surface. Now, I would like to give you some examples of this. One of them is the thermoformable PET for the in-mold electronics, which is used a lot in HMIs for the automotive and medical applications, for example. And it replaces the incumbent polycarbonate films. The advantage of PET here is this is much more chemical resistant and offers a better flex resistance than polycarbonate, and yet meeting its formability performance. Then we have flame retardant PETs, which meeting VTM 0, and we hope to get them on the market this year. Another more recent development for flexible electronics is the inherent clean and defect-free films, which we are manufactured with a peelable sacrificial layer, which you peel off the PET substrate to leave it with a pristine, clean and smooth surface, which allows you applications which demand a very high resolution structure and therefore absolutely no defect whatsoever on the surface. But also, and that's what's being more developed at the moment, is it meant a breakthrough for development of monolayer ultra barriers. And this leads us nicely into the encapsulation development project, which is mainly driven by flexible PV applications in particular at the moment. Going to that, what you see here is a device, a PET with an electrode, and you build a device on that needs to be encapsulated by a substrate, barrier substrate, which is a defect-free substrate, and you put a metal oxide on it. This metal oxide, after it's been unpeeled, very clean, very smooth surface, so you get a very robust layer. Then after it's being deposited, what we develop, and that's where it's quite interesting, we put a protective liner on it, which could serve as an encapsulant if need be. And then what we can do too is actually add on the other side of the PET an abrasion-resistant layer for OPV. That'd be interesting because it's often used outside and needs to be cleaned. So some abrasion resistance would be handy there. Further, if it's exposed to nature, we can.
Valentijn, just to know you have 1 minute.
Yeah, that's absolutely perfect. Add some UV resistance and hydraulic resistance to it, which makes it gives it longer lifetimes when exposed. And then further, we can structure the surface with to minimize the reflection, and maximize the light capture of it. Now, that is not just it. We can go further because usually these devices are encapsulated with these barriers. What we can do too is further enhance the rationalization of the applications in the industry by making it a hybrid solution with a electrode layer on top of it, on top of the protective liner, for which it needs to be compatibilized because it's not suitable for directly electrode. It needs to be adapted, and we can do that with DTF. We have a few solutions for that. And that will rationalize the design of an OPV module, for example, quite drastically. Okay, well, that's really what I'd like to say. These are about the highlights which we have with the developments. And we can take on many other challenges, and we very much look forward to work with you to realize the potential of your own innovation. And have you any questions? Like to see you in DTF room 8.